All right, so after hopefully anyone looking thoroughly at my video lessons on the general understanding of what a sampling distribution of the mean value is, then let's start bringing up a few examples here to enforce our understanding here. So I'm now going to start with example 1 here. So in example 1, we have a beginning description here, says mosquitoes. So notice there's a plural being indicated here. So that's indicating that here we're not aiming at only 100 mosquitoes, we're not only aiming at 1,000 mosquitoes, we're aiming at a very large amount, an unknown but very large amount. So my idea, the idea I would like to enforce here is that this is the population of individual mosquitoes. So now let me continue. So mosquitoes are known for an average lifetime of 7 days with standard deviation 3 hours. And 3 hours is 1/8 of a day. So 3 hours is better to be understood as 0.125 of a day, because this is 1/8 of a day in decimal. And so now, assuming mosquito lifetimes are normally distributed. So here's the actual question, part A of our example. A sample of 25 mosquitoes is collected. Find the probability that mean lifetime of this sample is above 7.08 days. After looking at the wording description of the problem, what we must realize is that now from the population of mosquitoes, we have a population of mosquitoes. So I'm going to use a capital letter X as a random variable to represent, this is the, so X is to represent the lifetime of a mosquito, of any mosquito. And so from this population, what we know is that mu equals 7, because according to what it says right here, from the beginning description of our problem, mosquitoes are known for an average lifetime of 7 days. That information gave me my known population mean value. And further, I know I'm going to have a sigma value, which stands for a population standard deviation value, being 0.125. I know this value because back in the wording of the problem, it says, and being part of the description of our beginning population here, that mosquitoes are known for an average lifetime of 7 days with standard deviation 3 hours, or better way of understanding that, 0.125 of a day. And that's the reason how I know that we have a sigma value from our beginning population. And so after thorough discussion in the lecture regarding sampling distribution, the idea now is that we are from this population, we are picking samples. So each sample is being, so now that information here is done for now. From each sample, we select 25 mosquitoes. So 25 mosquitoes in this problem is only one sample, but our sample is not the only sample. We can have infinitely many other samples. And so in that way, since we realize now that our sample here is not the only sample, in this sample of 25 mosquitoes, we may have our own sample means. But outside of our sample, on other samples out there, provided they're all at the same sample size 25, then we can generally regard to all of those sample means, because our sample can have a sample means. Any other samples out there outside of our sample, we also have their own sample means. So now we generally regard to all of those sample means from each sample of 25 right here as a random variable capital X bar. Many textbooks in the market out there only use the symbol capital X bar, but I go ahead and step forward and indicate a subscript 25 here is to indicate that this random variable represents a sample mean. Okay, so this random variable is once again represents the lifetime of one mosquito, but this is the lifetime, the average lifetime after we average out 25 mosquitoes in each of our samples. And so to formulate the definition of our capital X bar 25 right here, I'm going to say capital X bar 25 represents the mean lifetime instead of one single lifetime value of one mosquito. This is the mean lifetime or the average lifetime of a sample. Of 25 mosquitoes. And so now this recalls that idea we have learned about what we have here is outside from that population in the beginning. Now we have realized that our sample mean in here belongs to a completely separate population, but as big as the beginning one right here. But it's a separate population where each data value is a sample mean lifetime from a sample of 25 mosquitoes. Okay, and so because of the nature of this random variable right here, we can have infinitely many values. So now back to our question. That's why we have the kind of problem where, hey, if we now pick up any sample, then what's the chance, what's the probability that our sample that we picked up, represented by the random variable capital X bar 25, we want to find out what's the probability that our sample has a sample mean being above 7.08. So I just now briefly explained the reason why we have this kind of problem as a probability, simply because there are infinitely many values of sample means out there, and each one of those samples is out of 25 mosquitoes. And that's how the question is being worded here. Find the probability that the mean lifetime of this sample, of any sample that we picked, is above 7.08 days. All right, so now back to our writing board right here. So now once we realize our goal here is that any sample we picked up is not the only sample. There are infinitely many other samples. That's why we want to find out how much chance our sample here has an average being above 7.08. And so at this point, this average is not the same as this average. I hope anyone is being clear about this. This is the average that's if we go after the entire population of individual mosquito lifetimes, then this is the average. But this is only, we're looking for, hey, in a sample of 25 mosquitoes, what's the chance that our sample we picked up there will be above 7.08? Okay, so now once we realize that we have an entire sampling distribution of sample means for mosquito lifetime right here, then as I have explained in my general lecture, then this population, this distribution right here will also have a center and an average spread as well. So now I'm going to indicate what to know. So what to know about, because we already knew about the beginning population, but this brand new population where the data is represented by the sample mean, where each data value is a sample mean, then there's something we need to know over here. The average for this population is namely the mu x bar that I have explained thoroughly back in the general lecture. And so now generally it's proven in a theorem, but now for our class right here, for the practicality of our work, we don't need to look in depth at the theorem itself, but there's a theorem that guarantees that this mu x bar value, supposedly the center of this population, will be equal value with mu, the known population mean from our beginning population. Now, so anyone at this point is probably noticing that I start using the term beginning population quite oftenly here, because the idea now is that this is the population where we picked samples from. I can pick a sample, but anyone else can pick a different samples. But all samples are being selected, being picked from this beginning population. And so this beginning population already had a known population mean. But now once we know that our sample that we picked belong to a separate population, then this population here will have an average, a center as well. We call that namely the mu x bar. It's the average of all sample means. But now it's proven, this result is proven that mu x bar will equal value with mu. So that means the good news for us now is that mu x bar in our case will equal 7. So final conclusion here. What we need to know about this population, the center will equal 7 as well. Now, the next thing to know about this population of sample mean values of size 25 in each sample is that the average spreading or standard deviation of all sample means, symbolically written as sigma x bar, the average spreads on this sampling distribution of all sample means, then it is known, it is proven as a result that we can find this sigma x bar values easily by doing the math. From our known sigma value, we are going to divide by square root of n. And n here is our designated sample size being indicated here. So once again, I know that our sample size here is being 25 simply because back in the reading of the problem, it says a sample of 25 mosquitoes is collected. So being collected from where? From our beginning population here. But so now our sample here is only 25 mosquitoes, and that means it belongs to an entire population of all samples where each sample is only 25 mosquitoes. But so now capital letter N, to be clear, is the sample size in each of our samples. And so in this case, we can have a calculation. Beginning population had a known or has a known standard deviation of 0.125. So here we can just simply do a calculation. 0.125 as that was in our beginning, from our beginning population sigma. So this sigma here has no x bar, as I have already explained in my general lecture over here. And then now we're going to divide by square root of 25. So calculation comes out to be 0.025. And so when you're actually doing any assignments or doing any work here, watch out from your instructor, or watch out from be aware from your whoever asks you to do this kind of work here for the rounding requirement. So be fully aware of the rounding requirement for each problem that you are working with. But so now, so we have found, this is what we know about our sampling distribution of the means right here. We already knew the center. This is center, a very important information. And all this here is useful for us because this is the average spread of our distribution. And now there's one further valuable information we need to know regarding our sampling distribution of the means that of the sample means that we're currently working with right here. Now, the distribution shape, because as I have explained in our general lecture over here, any population has a distribution shape. So as soon as we realize that what we have here, what we are working with here, is a population of data, the population of data that contains sample mean values, then this population will have a distribution shape. And so what matters for us now is that we want to find out whether or not our distribution shape here will be on a bell curve or not? Or in other words, can we put this data on a bell curve? That's what will be, that's what's valuable for us. And if it would be, then it's going to take 7 as the center and 0.025 as the average spread. And so recall again, this was our mu x bar that we found out earlier, and this value 0.025 is our sigma x bar, average spread on our distribution. But we are still at a question mark right now, that's whether this distribution shape, a nice bell curve, will be true for our current sampling distribution right now. And so the answer to this as a yes or no question goes back to this, draws back to some information regarding the beginning population. So now I'm going to need to also write down a third piece of information regarding our beginning population. Now, back to the wording description of our example. This statement right here, this piece of small statements before we jump into our description of the sample. So everything in the everything before part A of our example describes the population. And so including this piece of information, assuming mosquito lifetimes are normally distributed. This piece of information, according to what we have learned before, this is an indication that our beginning population, our beginning distribution of mosquito lifetimes, it was already known to be a normal distribution. So this data, this population was on a bell curve. Another way of saying it, it was on a bell curve at center 7, but with sigma 0.125. And so notice how these two populations have different sigma. And I also explained that thoroughly back in my general lecture regarding what a sampling distribution of the means is. Because it makes sense that way. Maybe they have the same center, but they definitely have to have different standard deviation, because in the end they are different populations of value. But now this is some further known piece of information from our beginning population data. And so now the answer to this, back to the question that we were in the middle of finding the answer as a yes or no over here. Now I'm saying yes. We now can say that this sampling distribution of the means right here, this population of all sample means will be on a bell curve. And that bell curve will take center 7, the mu x bar, and sigma x bar as average spread, value here being 0.025 right here. So the reason that I can just simply saying out loud that this distribution automatically came out being a bell curve, and I said yes right here simply because as long as our beginning population was known, so as long as we had this piece of information known from our beginning distribution, then anytime we're picking up a sample, then our distribution of sample means will be always a bell curve. All right, so now in the end, what is good about what we knew? We already knew that this random variable representing our population of sample means, capital X bar, is on a bell curve. This is what's known, and the explanation was given earlier. Center of the bell curve is at 7 and 0.025. And so now here's the reasoning. Once we have found out that our sampling distribution of the sample means here is on a bell curve like this, now we can go ahead and draw for ourselves a bell curve. A nice bell curve. And the center of this bell curve now is 7. And this bell curve, any value being placed on this horizontal line right here is a sample mean value, a sample mean that came out from a sample of size 25 mosquitoes. And so, generally speaking, the random variable being represented here is capital X bar 25. Okay, And so now the whole point now is that the whole point of knowing whether we have a sampling distribution being on a bell curve is that we can now bring ourselves back to a problem where we're working on a bell curve problem. And so now on this bell curve, back to the actual ultimate question, we want to find the probability that any sample we picked up would fall above 7.08. 7 is right in the middle of this bell curve here, and I forgot to indicate this bell curve has average spread represented by sigma x bar to be 0.025. So now on this bell curve, 7.08 is about somewhere to the right hand side of 7. And this 7 here, even though equal the same value with mu, but really it's this value here. I highly recommend anyone viewing this video to understand this as mu x bar, because all the times mu x bar will equal value with mu. And so now the actual probability problem here is represented as a shaded area or a shading area to the right hand side of 7.08 on our sampling distribution bell curve. And so now from that point on, now we're just simply back to a problem where we're finding an area on a normal distribution bell curve. So back to the standard work. So this is a sample mean value that we expect to be above 7.08. And so now, again, 7.08, I am going to subtract the mean in the center of the bell curve and divide that difference by 0.025. So the work I'm doing here is in the attempt to find the z-score for 7.08. And so now calculation gives me z-score for 7.08 is a positive 3.2. Okay, so that means if this was the standard normal distribution bell curve where center here is at 0 and 7.08 is equivalent to 3.2, then this area here, the probability representing the probability that we find a sample mean above 7.08 will be the same as the area on the standard normal distribution bell curve where z-score is above 3.2. So now the work comes back to the kind of work that we have been familiar with. So now to find this area on our standard normal distribution bell curve, we are going to run our normal CDF command right here. Notice how this interval doesn't have an upper end. It does have a lower end, but doesn't have an upper end, or in other words, it has an indefinite upper end right here. So now I'm going to go ahead and switch over to my calculator. And at this point in our learning quarter here, then I'm assuming that viewers or students who are studying with me already well familiar with the differences, how slightly difference between the different versions of the TI-83 and 84 calculators. So allow me to only focus on whatever the software I have right here, which is the newest version of the TI-84 Plus, and the emulation here is called the CE version. But so anyway, the way to find our normal CDF command remains exactly the same. Second, variables. I'm scrolling down to option number 2, normal, that says normal CDF. I'm going to hit enter. And so since we have a finite lower end, that would be at z-score 3.2. And then our upper end here is the indefinite upper end. So I'm going to go positive 1 E99. And just like any other time before, we are only running this normal CDF, at least for students in my class. I want my students to only operate this command on the standard normal distribution bell curve. That means we are going to default these two values to 0 for mu and 1 for sigma. And I'm going to hit enter a few more times. And so now Again, just a quick brief back, but TI 83 or early 84 calculator users will have the command normal CDF command being directly printed on your screen instead of a menu like what you have seen earlier. And then all you have to do is just simply go ahead and type in your values with comma, so low end, high end with comma between, and then comma with the mu defaulted at 0 and comma 1 for standard deviation defaulted at 1. And now we are ready for executing our command. So this value over here, that's the way how the calculator is giving us the answer, but that means, so now I need to go back to my writing board. But that means the answer there, this area in real-time decimal, it's a 0.000687 and a lot longer. That's what the 6.87202 and a lot longer E-4 as you have seen on the calculator screen means. But now we can just simply, after we understood what it is, we can just simply write it down in decimal. And as I keep mentioning in many lectures already, and it would be the same here, unless being specified otherwise, I'm going to round I usually round my final value, which is right here, in 4 decimal places. So the final answer here is 0.0007. Okay, and in case we are asked to express our final answer as a percentage, then this means the chance to find, now, so we picked any sample of 25 mosquitoes, and the chance that our sample there has a sample mean being above 7.08 is only as a percentage. Maybe it's easier for somebody to realize, but it's only 0.07% chance. That means 100 times, it's not even half percent to be above this sample mean value like that. Or in decimal, it's 0.0007. And so now, before we are moving out of this particular problem in the current example and heading out for another question right here, let me quickly make a generalization right here. But for many of our later examples, generally speaking, we are in the kind of problem where we want to find the probability where our sample mean, okay, where our sample means at a given sample size. And again, I mentioned earlier, indicating the sample size here as a subscript with my capital letter X with bar here. It's just my own choice, but and many textbooks in the markets out there don't have this, but it's just the same kind of problem there. But so now we're just looking for either our sample means being in an interval of value. So the chance that capital X bar is in an interval of value. Okay, so that's mainly the goal of the problem right here. Just like here, we want our interval of values here is anywhere above 7.08. You might run into other kind of problem, but you might run into other problems, and that's slightly different indication. But in the end, we want to find a probability that a sample mean value is in a given interval of values. And then what we need to know about this before we can actually solve the problem, we need to know mu x bar, because now once we understand that what we have here is a sampling distribution of the means, of the sample means, then this is a population. So mu x bar is the center for that population. And what's valuable about the steps we have learned here is that mu x bar will always equals mu. And mu is always the known population mean from the beginning population. We will always know how to calculate sigma x bar, the average spread on this sampling distribution, by following the formula known sigma divided by square root of n, our sample size capital N right here. And then we generally find a way, and then we generally try to find a way to put this we want to find out if this capital X bar is on a bell curve or not. That's what we want to do, because once we can put our problem on a bell curve, then this problem can be done as an area problem on the bell curve. So these are the three key steps, and once we've gotten this key step, then we can always draw the bell curve and start doing the usual calculation on the bell curve problem with the normal CDF command. So these are always the three key highlighted steps right there. So I'll just have to add that. Find out. So find out if this is true or not. Find out if our random variable capital X bar subscript n is on a bell curve, the normal distribution symbol. And now we are ready for looking at another problem being treated as a different part in the same example here. And so just a word before we getting further into this actual new problem right here. But since I have given enough details in the earlier part of the same example, and here it's just a repeated opportunity for anyone to see how the problem can be carried out again. So allow me to start speeding up the pace, and as well as just simply highlight on the key steps right there. Okay, so now quickly reading into the wording description of the problem. Again, we're looking at mosquitoes are known for an average lifetime of 7 days right here. So all this information, it looks like it stays the same. So with standard deviation 3 hours, which is the same as 0.125 of a day. So we know that we have a population of individual mosquito lifetime, and then they're all average out being 7 days. And standard deviation is 3 hours, or 0.125 of a day. And we further knew that mosquito lifetimes are normally distributed. And so that's what this line is for. And so in other words, now back to my writing board, and allow me to retain all that information I have developed throughout the earlier problem, because all that information regarding the beginning population remains the same. And now from this population of mosquitoes, I am now, instead of picking up 25 mosquitoes in a sample, here I am going to pick up only 16 mosquitoes in each of my sample. And so a sample of 16 mosquitoes is collected. So as I said earlier, instead of 25, now I'm only picking up 16 mosquitoes in each of my samples. And so now, pretty much it's the same question here. Find the probability that the mean lifetime of this sample is above 7.08 days. And so again, having all that information regarding the beginning description retained here, then again, when we're looking at our sample being regarded in this part B of the example, then now we know that we have a sample size being 16. Or in other words, in each of our samples, there are 16 mosquitoes. And so further, what to realize now is that we're not simply just picking up one mosquito, but we're picking up a sample of 16 mosquitoes. And our sample will give us a sample mean. But now we have to realize further that the sample we have here, that we pick up here, is not the only sample. Our sample is only one among infinitely many other samples out there. And so the same with our sample mean here. Our sample mean, whichever that can come out, that might come out from this sample we have, is only one among infinitely many other sample means out there at sample size 16. And so for that reason, now I'm going to define, and the same with any textbook, I'm going to use a capital letter X with a bar here. So this is a new random variable. But in my style, I always indicate a subscript that's indicating the sample size. So this capital X bar 16 here is the random variable that represents the mean lifetime of a sample of 16 mosquitoes. Okay, and so now once we define that random variable, we must even further realize that this now is representing for us an entire population of sample mean values where each sample is of 16 mosquitoes, and any sample in this population is selected or collected from that beginning population. And so once again, because of that reason, we can have infinitely many different values for this kind of sample means right here. That's the reason why the problem here is formulated as, and as another way to explain the whole reason why we have this problem. Now we want to find out, now if we just simply picked any sample, then what's the chance that our sample, as one among infinitely many others, will have sample means greater than 7.08. And so even though being treated as a completely independent problem, but you can see that I purposely brought up this problem where the number here is exactly the same, except for this random variable we are doing now. This sampling distribution of the sample means here is completely different sampling distribution of the sample means that we worked in part A. But this is, so here we just simply want to find a chance that our capital X bar, any sample mean that we picked out of 1600 mosquitoes, is going to be greater than 7.08 days. So now, learning from all the key steps right there, then what I know that I'm looking for the probability that our random variable is in an interval of value. But now I need to know what mu x bar value this sampling distribution must be. So mu x bar, the center of this sampling distribution, must always equals mu, which is in this case 7, because mu was already known to be 7. Our average spread on this sampling distribution, symbolically sigma x bar, or formally this is the standard deviation of all sample means that we can find, can be quickly calculated as the given sigma from the beginning population, 0.125, divided by square root of the sample size. And since our sample size here is currently indicated in 16, then here we divide it by square root of 16 here. And so now sigma x bar is making it clear that we're working with a different problem from part A. Calculation comes out to be 0.03125. And again, here I'm using full precision of my calculation, but in every problem, make sure anyone doing these kind of problems to watch out for different rounding requirements. So now I've completed the two key steps here. And now again, since our beginning population, where we picked any samples from, is a normal distribution, or another way of saying a bell curve data, then so that will automatically imply that this sampling distribution of ours, completely understood as another separate population, will also be automatically a bell curve data. So this will be N7, or in other words, we're saying that capital X bar 16 is normally distributed. That's what the capital N is for, normally distributed. We can put all of these sample mean values on a bell curve with center at 7. But sigma here is 0.03125. And that means we can now draw a bell curve. And later proceed this calculating the answer to this problem as entirely as a bell curve problem. This bell curve has center as we have found out center at 7. And any value on this line is a sample mean of 16, a sample mean lifetime of 16 mosquitoes. So represent generally as a capital X bar 16. And then we want to find the chance that our sample mean will be above 7.08. So 7.08 on this bell curve is somewhere to the right hand side of our bell curve center. And so this problem, once we have approved that we have a sampling distribution being on a bell curve, then treating this problem as a bell curve problem, we can now just go ahead and shade the area to the right hand side of 7.08. And then again, this bell curve here, unlike the bell curve we have seen in part A, this bell curve has average spread, symbolically sigma x bar to equals 0.03125. And so now, realizing that we're putting ourselves back to just an ordinary bell curve problem where we just simply need to find an area on the bell curve, then recall that we need to find z-score of our value here. So our value here, our low end of the interval is at 7.08. So let's find z-score of this low end of the interval. 7.08 minus 7 divided by our current standard deviation of the bell curve here is being 0.03125. So now I'm dividing that by 0.03125, and our work here is to find z-score for this low end of the interval. And so now calculation will come out being 2.56. Positive 2.56. So that means this area on our current bell curve shaded to the right hand side of 7.08 is equivalent or is equal to the area on the standard normal distribution bell curve where we're shading to the right hand side of z-score 2.56, or formally speaking, this probability here is equal to the probability on the standard normal distribution that we find a z-score greater than 2.56. And now getting the final answer here is just a matter of running the normal CDF command. So now on my calculator, on my standard TI 83 and 84 calculator, I am going to again make the key combination second variables to retrieve my distribution functions for stats, and scroll down to option number 2 that says normal CDF. Click enter. And so this time on on the writing board here, this interval is indicating that we have a low end, a finite low end, but an indefinite upper end here. And this low end is corresponding to z-score 2.56 on the standard normal distribution. And this value here, supposedly mu x bar, is at z-score 0. And so now, with all that understanding there, back on the calculator, for lower end, we are going to enter 2.56. And the high end, the upper end being an indefinite upper end, we are going to leave it 1E99. So 1E99. And again, for all students who are studying with me, I only want my students to use this normal CDF command on the standard normal distribution. So that means all of these values are in respect to z-scores, and further we default these two values to 0 at mu and 1 at sigma. So now I'm going to hit enter a few more times, and here we are ready to execute the normal CDF command. So here's the answer for that. So that now means the area shaded to the right-hand side of z-score 2.56 on the standard normal distribution, or the area shaded to the right-hand side of our 7.08 on this current bell curve here will be equal to 0.0052336 and a lot longer. But as I have always been saying, unless being specified otherwise, I will usually round my answer to 4 decimals. So in this case here, I'm looking at 0.0052, and that is my final answer for this problem. And in case our final answer is required to be in percentage, to be expressed as a percentage, then this answer here is equivalent to or equal to a 0.52%. And so that means as an interpretation of this answer, maybe it's a little easier to look at the percentage here. But what it says now is that anytime we're picking a random sample of 16 mosquitoes from the set above population, then the chance that the sample mean in our sample that we picked being greater than 7.08 is calculated to be only a 0.52% chance. It's just barely above half of a percent.